In this lesson, we'll talk about substitution with logarithms. I recommend letting u equal the denominator. So we get x squared plus 1, meaning du is 2x dx. And so du over 2 equals x dx. We've got our u here, the x squared plus 1. And so now let's just analyze it. X dx is part of my du. As I've mentioned in the past, anything for du cannot just be grabbed out of the denominator unless it were actually written in the denominator like a fraction for your du equation. But since it's in the numerator, x dx is right here. That's an x dx in the integral. So that becomes du over 2. Let's make our substitution. The over 2 I'll put in front. X dx all became part of du. And so I need a placeholder. U is in the denominator. So I'm going to do 1 over u. It was in the denominator before. It needs to stay in the denominator now. Du. We get 1/2 natural log absolute value of u plus c, which is 1/2 natural log of the absolute value of x squared plus 1 plus c. I will tell you, there are some strange circumstances where you would be allowed to drop the absolute value, and this is one of them. The reason being is that x squared plus 1 is positive no matter what, so the absolute value doesn't really do anything here. Next example, 1 over x natural log of x. We could let u equal x natural log of x, but that makes a pretty big mess to take the derivative. That's a product. So I'll give you a little tip here. If you ever have, say, a lonely x in the denominator, and natural log of x shows up somewhere in the problem, you should let u equal natural log of x, because the x sitting there in the denominator like that is a perfect candidate for my du, which is 1 over x dx. We get u here, and then we get du from right here. Think about it. 1 over x is an x in the denominator. Dx is at the end. And so this x in the denominator coupled with the dx does indeed make du. So we get the integral of 1 over u, and the x in the denominator with the dx gives me du. Okay. So we get the natural log of the absolute value of u plus c. But since u is natural log of x, it really is the natural log of the absolute value of the natural log of x plus c. It looks kind of funny to see it that way, natural log of the natural log, but it certainly makes sense to talk about that. Next example, we got x over x minus 1 squared. Now if you want to, you can let u equal x minus 1 squared, or you could let u equal x minus 1. There's actually two different ways to solve this problem. I would like to go with, for the sake of example, u equals x minus 1. Then du, the derivative of x is just 1, so we just get dx. Du and dx are the same, so I get u. I'm going to have a u squared in the denominator, but I still got that extra x floating around. But I'm really going to need to change this to x equals u plus 1 to get a little bit more information. So this x becomes u plus 1, dx is just du, and now we can make our full substitution. We get the integral of u plus 1 over u squared du. We need to split this up as we've done in the past. U over u squared plus 1 over u squared du. That's the integral of 1 over u plus u to the negative 2. Don't start getting trigger happy on your logs. U to the negative 2 is what's going on here. Anytime we have a negative exponent, we use our old rules. We get the natural log of the absolute value of u, and then the power rule says add 1 to the power, divide by the new power, and get a plus c. Let me write this as natural log of absolute value of u minus 1 over u plus c, just using a little algebra. And finally, let's back substitute u becomes x minus 1 on both of these, and this is our answer. Next one. Let's let u equal the denominator this time, 1 plus e to the x. Then du would be 0 plus e to the x, so just e to the x. Let's see what we have. Here's my u, and my du would be, since it's in the numerator, there's my du. And then we've got to change the limits, which I'll do in a moment. But the e to the x dx becomes du. U is in the denominator, it needs to stay in the denominator, so 1 over u du. Now to change our limits, let's plug in 0 into this equation to get 1 plus e to the 0, which is 2. And u of 1 is 1 plus e to the 1. We're just going to leave that as 1 plus e. Natural log absolute value of u comes out of this integral. So we get that evaluated from 2 to 1 plus e, which is natural log of the absolute value of 1 plus e. You really don't need the absolute value there, since 1 plus e is positive. And the natural log of 2. We'll just leave it like that. Let's do another example. This one is just to put some perspective on what we're doing. Find the area under the curve y equals x over x squared plus 4 on the interval from 0 to 2. Remember, the area under the curve is a definite integral. From 0 to 2 is what we're given. And we get the new function, x squared plus 4. Let's use a u-substitution. So we got u equals x squared plus 4, so du equals 2x dx, and I'll divide by 2 since I don't have a 2x. I get a u, and I get x dx becomes du over 2. And I need to change my limits, so I'll tackle that in just a second. We got a 1/2 in front from the du. The x and the dx become just the du, so I have 1 over u du. I need to change my limits. U of 0 would be 0 squared plus 4, which is 4. U of 2 would be 2 squared plus 4, which is 8. We're going to go from 4 to 8 here. That gives us 1/2, and the integral of 1 over u is natural log absolute value of u. Evaluated from 4 to 8, so we'll plug it in. 1/2, and then remember, the absolute value of 8 is just 8, the absolute value of 4 is just 4. So I get natural log of 8 minus natural log of 4. And if you'd like, you could clean this up. This answer is fine. But remember your rules of logs. This is really the natural log of 8 over 4. So we can call this 1/2 natural log of 2. And even more so, you can say natural log of the square root of 2, if you'd like. But either way, this answer right here was fine. Let's use our new tricks, and let's get ourselves some new integration formulas. These are some rather standard techniques that come out, but they work out much more differently than you would think. What I need to do is, first off for tangent, write it as sine x over cosine x. With that said, we'll solve this integral. Let's let u equal cosine x. Again, the denominator is generally a good choice. So du equals negative sine x dx. And I do have a sine x, but it's not negative, so let's switch the negative sign. And now we're able to give ourselves a rule. Cosine x is my u. Sine x dx is my negative du. And so let's use the substitution. I'll bring the negative in front. We're left with 1 over u du. So as we've gotten accustomed to, we get the negative natural log absolute value of u plus c. And so just put cosine back in. We get negative natural log cosine x plus c. Now this is the usual rule. However, you can also talk about it by distributing the -1 and flipping the inside. Natural log absolute value secant x plus c is often one that you'll see as well. That's a new rule. That's the integral of tangent x. It has a natural log in it, which is why we've yet to do it until now. Secant x has a really weird trick. What we do is we multiply top and bottom by secant x plus tangent x. Seems strange, but I'll explain to you why in just a moment. When I plug that in and I multiply across, think of secant x over 1 if you'd like. I get secant squared x plus secant x tangent x divided by, I'm going to reverse the order of this, tangent x plus secant x. I got a dx. So here's what I want you guys to notice. Tangent x plus secant x has derivative secant squared x plus secant x tangent x. That's in the numerator. So u equals tangent x plus secant x. Then du equals secant squared x plus secant x tangent x dx. This is why we even did that step of multiplying by that strange object. It just works out. This turns out to just be du in the numerator and u in the denominator. So we get natural log absolute value of u plus c, which is natural log of, let me write it the other way because that's the more standard one. We'll do secant x plus tangent x plus c. That's our rule for the integral of secant x. The last four are given by these formulas. Tangent x we just found to be negative natural log cosine x plus c. Secant x we just found to be natural log of absolute value secant x plus tangent x plus c. Now the other two, using similar techniques, we get that the integral of cotangent x is natural log sine x plus c, and the integral of cosecant x is negative natural log of the absolute value cosecant x plus cotangent x plus c. So now we've got four new integrals that we can learn. What we're going to do for this one, we've got secant square root of x over square root of x. Now, you've been in the habit of choosing u being in the denominator, but don't get too much in the habit of that because that's not the technique that works all the time. Remember, if you've got something inside the function, you should generally let that be u. I'm going to let u equal the square root of x. My u is chosen from the inside of the secant. Du equals 1 over 2 square root of x dx, and I have the over square root of x part. Let's multiply both sides by 2 to make this a little nicer. This part is going to become 2 du, and so I end up with a 2 in front, and the integral is just secant u du. So now we look at our rule for secant x, the same rule will apply for u. So 2 times the natural log of the absolute value of secant u plus tangent u plus c, and back substituting I get 2 natural log absolute value secant square root of x plus tangent square root of x plus c. That's our integral for the natural log function. Next two examples are for you to try, and these will use the secants and tangents and so on. They are for you to try, so please feel free to pause the video and try it. Alright, hopefully you guys did try it. For this one, I'm going to let u equal x cubed. Good choice because it's inside the tangent function. So du equals 3x squared dx, meaning du over 3 equals x squared dx. We've got a u, and x squared dx is my du over 3, right? The over 3 I'll write in front. We're left with the integral of tangent u du, and so now we can use our new rule. The derivative for tangent u was negative natural log of cosine x plus c. And so I put the negative sign in front just to make this a little easier. And so we get negative 1/3 natural log absolute value cosine of x cubed plus c. Hopefully you guys are doing okay on these. Next one. Let's let u equal the whole denominator, because this time that seems to be the best choice. We'll let it be tangent x plus 1, so that du is secant squared x dx. Nice. Because my u is in the denominator, my du is right here in the numerator. No changes needing to be made. So I just get the integral of 1 over u du. That's the natural log of the absolute value of u plus c, which is the natural log of the absolute value of tangent x plus 1 plus c. Hopefully you guys are getting the hang of these. Now we've got some integral rules. We have the tangent, secant, cosecant, cotangent rules, as well as now 1 over x or 1 over u can become natural log of x.